All right, good afternoon. How you guys feeling? How'd the exam go? Okay. It's like anytime if I give an exam in person, if I ever tried to ask somebody in that moment, it's like totally a bad idea. Nobody's going to be in a good mood. Nobody's going to be feeling good about it, even if they did perfect. So it's always interesting to think about, like, as people are passing in exams and like done, they just their brain has been in hard mode for a while, and now they just want to be away and not talk to me. Uh, almost always. So it's always kind of funny. Even just one day, changes a lot, even if you know, no matter what the exam was like. So, but any major issues, concerns? Okay. So, as is my practice, I do plan to go back over that with you at some point. Grade it first, give you the feedback, and then go over it with you. A couple changes to the syllabus. I realized today, as I was kind of checking in on where we were missing today. So just wasn't there. But we are having a lecture today, so thanks for showing up. So I updated that, shifted things around. And then I also realized I need to travel on the 25th, which is, will this open? No. Tuesday the 25th, that's the Tuesday before Thanksgiving. I have to go to a visa appointment early on Wednesday that week. So I'll be traveling and won't be able to make that class. So what I'm proposing, if you guys agree, give you a little extra flexibility for your Thanksgiving break, is to delay the exam 2 recap and make it online virtual, probably the Friday before Thanksgiving. That way, if you aced it and don't care to show up, you don't have to. And I'll probably just lecture remotely from my home office. And you can tune in if you wanted to ask questions live, and that would be totally fine. So does that sound like a good idea? Happy about that? Anybody hesitation? You're also welcome to email me if you have some concern. That way we keep on schedule. I give you that there, and we keep our typical content in person, assuming that we have all these in person, which I think we will. Okay, so that's my plan for now. Just a side note, I'm also doing that for my other course, same type of deal. So if you tuned in at the wrong time, you might be a little confused as to what we're talking about exactly, or I didn't think that was on the exam. What did I miss? So I will provide some information about the timing of all that as we get closer to time. Okay, and if you had any strong preferences, feel free to let me know, because I think my day is open and I can't accommodate the other class in terms of what they feel like, but you guys are small enough that if somebody really wanted it at 2 p.m., I could probably just say, why not? 2 p.m. So let me know. All right, so with that, today we are going to be talking about precipitation reactions. And I also wanted to go ahead and take a few slides from something we didn't quite cover in the adsorption section, and that would be a bit of the surface chemistry. So as we are moving from the kind of physical removal of contaminants into chemical removal of contaminants, I wanted to touch on kind of the borderline, some of the surface chemistry that touches a bit of both. And whereas we're really focusing on kind of soluble contaminants, we can also certainly consider colloidal particles, which are kind of soluble or kind of act soluble, but they are particulate matter. So that's another piece here. So let me pull up the lecture and we will get going. All right, so like I said, starting with surface chemistry as kind of a bridge between particles, solutes, surfaces, all of that. And to bring in one of the topics, the core topics of water treatment that is relevant would be the process of coagulation and flocculation. So many times, if we are dealing with particles, we want to generate larger particles to let them settle, or to at least destabilize them so they would stick to some other surface. Maybe we're doing granular media. We want them to be able to stick to the surface and not have a repulsion force away from the surface. So we want them to be able to meet the surface and stick. We talked about adsorption in general. Much of that has to do with molecules, which that doesn't quite apply so much, but it can also apply to particles. So we're going to talk a bit about the chemistry, the surface chemistry involved with giving a surface a charge. How does that happen? Why is that important? I'm not going to really get all the way into sedimentation, flocculation. If you are interested in that, I have plenty of materials. That is certainly a physical and chemical process in water and wastewater treatment, and I have taught on that before in the way I've structured this class in the past, but I also teach it in the undergrad version. So if you want more resources, I can definitely help you there. For now, I just want to cover some of the principles of why a surface may change or may matter there. And ultimately, for the flocculation, our typical goal is to make larger particles. Therefore, we are reducing the number of particles as they stick together. 2 become 1, 5 become 1, and you get fewer particles, but larger particles is the idea. Okay, so why does a surface have a charge? You may have noticed, I've probably talked about it, maybe you've heard from other classes. In water, you typically have some ion that we know, okay, ions can have charges, that's kind of the definition. They would rather hang around with a few extra electrons to fill out their valence, and therefore, given that they have X number of electrons and X number of protons, if they are happy, they'll just be hanging out with some negative charge or positive charge or whatever. However, when we come to some material, that's not exactly how it would work. And so there's a question, why does the typical surface have a negative charge in water? That's like the default or typical thing that will happen. So we can take a look at a few reasons. One would be what are called isomorphic substitutions. This would apply to minerals like clay minerals, like metal oxides. So if you take this silicate here, the Si with 4 oxygens, and you substitute one of the silica atoms with a magnesium atom, they're relatively close to the same size, but Si would have a +4 charge and would be balancing against 4 oxygens. Now you have a +2 charge balancing and all that. Well, the net charge difference from that substitution is a -2. So if you make a substitution like that, which can kind of happen randomly, you could also intentionally make it happen, well then you have introduced a net -2 charge to the system. So if you have one of those for every, 1,000 repetitions of this mineral structure, then you're getting some net negative charge on average. Of course, you could have much more than that. Maybe it's in every unit you have one substituted and you get quite a negative charge. If you take some aluminum oxide and you add an Fe there, of course you get a negative there. Same principle. So if you have some clay mineral that's assembled from a lot of either of these types of materials, that substitution can confer a net negative charge. So that would be isomorphic substitutions. You're basically keeping the same structure overall, but in some spots you are having a substitution giving you a charge. Well, there are other ways in addition. We could take a look at the functional groups at the surface of an organic molecule, or maybe you take an organic functional group and add it to something inorganic. That could also happen. And what we can say is we could take a look at just one segment, one moiety. That's a fancy term for a segment of a molecule, right? It's some branch, it's some functional group, even maybe this. So if you have some random natural dissolved organic matter molecule here, who knows what exactly that molecule is, but it's some random molecule, maybe that's part of what's in your tea, right? Some tannic acid, some molecule there. Well, the functional groups can infer a negative charge based on simple acid-base chemistry, because we might have some surface we'll call S with the 3 bars. We could call that a surface site. So if on that surface site we have some particular chemical moiety, some particular functional group, whether we're calling this S the rest of the molecule, or whether this is some surface, maybe we functionalize a silica bead, okay? Maybe we functionalize it with some particular organic group. In either case, now that we have something on that surface site, it could be something like an OH2+. Under acidic conditions, this would be likely to have the plus charge. At more neutral conditions, it would be likely to have the OH, or at basic, it could have a minus. So this would be the protonation-deprotonation reactions, and these would be equilibrium reactions. We're going to talk more about them in a few minutes. So for example, this guy would be in equilibrium. If we add H+, we would end up with the OH, the hydroxyl group, just by itself. So each of these we could describe with equilibria equations, and they'll be pH dependent. And it turns out that the pH at which these reach an equilibrium tends to be on the lower side of the pH scale, so many of them will have the negative charge at neutral pHs. Okay, these would also be known. This is also, let's say, we've probably seen pKa, so the dissociation constants, or just Ka. So each particular molecule is going to have an individual constant for where they reach the equilibrium. And like I said, many of these are such that at neutral or natural waters, many surfaces will end up with a net charge for this reason. If you add these functional groups that could get rid of a proton and then have a net negative charge. You could have the same in reverse and have positive charges. So this guy here, you could have this amine group, put it in the right conditions, and now you have NH3+. So you can have quaternary ammonium groups, things like that, that could give you a positive charge. They're just not quite as common. These principles are also how we end up finding or recognizing that we have what are called isoelectric points for a surface. Where, at what pH do we end up with the same charge or a neutral charge? Or you might also call this the point of zero charge. Or PZC. So you will see that in some literature, especially with regards to particles or some surfaces that you might be concerned about. And all of this can be quite important if you want to know how your surface is going to interact with a particle in the water, or it's going to interact with some molecule. If you have a charged molecule, it can become quite important. So if your pH shifts, maybe your molecule is still neutral, but now your surface is not. Or maybe your surface is now negatively charged, or let's see, and the thing that you wanted to stick on the surface is also negatively charged, so there's some repulsion. Maybe you can optimize it, find a pH where one is positive and the other is negative, and then there's some attraction. So these dynamics can play a role in many different scenarios. And if we consider this natural organic matter, we could call it, I guess it depends a little bit on the context. Usually if we're talking about wastewater, we don't use natural, we use just dissolved because it's kind of human impacted. But you'll see natural organic matter has NOM. That's not very M looking like. Or you'll see dissolved, just DOM. And so if we want to predict how well those are going to stick to some surface, how do we remove those with adsorption? We probably want to understand something about the surface itself, and then what's the typical charge or the net charge of these large molecules. And these can be quite variable, right? There's many thousands, probably millions, of different molecules that would consist of some class of dissolved organic matter. Stuff that bacteria produce, stuff that plants produce, degradation byproducts of all those things. A random assortment of large organic molecules is essentially what we're talking about. Some of these can get up to the colloidal size. Some of them may be a little smaller. Okay, so that's a kind of the surface charge type of situation, but there's also some other forces that are involved if we want to know whether or not two substances will stick, and the dynamics here. And ultimately the balance when we talk about stabilizing particles or destabilizing particles is really a balance between the forces that repel each other, and charge has the furthest stiff arm type of repulsion, or attraction if it's opposite charge. And then if you get close enough, then things start having much more attractive forces. We have what are called the van der Waals forces. These are not chemical bonding, but they are chemical properties that cause some bonding type of, so it's not like a covalent bond where it's now a new molecule. They can come back apart, so it's still that Velcro type of analogy, or maybe a magnet is a better example. So if you have two magnets, like refrigerator magnets right here, you won't feel them with each other. But if you put them really close, now you'll feel them. So that's probably a good physical example. And the distance to have them apart, the force drops off by more than a power of the radius squared. It's like the radius to the fourth or 6 or something. Same thing with the van der Waals forces. They're quite attractive once they're very close. So you'll see this in many examples. So the little water strider guys, it's the surface tension that's created. It's actually the molecules of water in contact with another, and it would probably be a repulsive force with their little feet. Then with a gecko, and so it's the water molecules with each other that are like providing some resistance force to that. That would be van der Waals between the water molecules and hydrogen bonding and stuff. Whereas this guy, he's getting his little feet pads, which are designed really well to escape any repulsive forces from electrostatic or others. And the little sticky pads allow for a very nice van der Waals type of contact and provide a pretty good sticking force on pretty much any surface, which is why they can go upside down on a very clean sheet of glass. Okay, so that's kind of where we see them sometimes in practice. We could provide a list of several different forces. You've got electrical dipoles, distortion of charge in neighboring molecules. So the way these electron clouds are interacting, not based on charge, but simply the proximity of the electron clouds can have an impact on one another. You can have what are called London dispersion. That's those electron motion within molecules. Hydrogen bonding. Yeah, so there's many other examples in addition, but that's where you kind of see them. So in particle stability, if you can cause particles to get over their repulsive electrostatic stiff arming, then these forces will take over. That's what allows them to stick together and become larger. It's also what will allow you to use a sand filter that's got very large pore sizes. So if a pore size is this big, you can catch a particle this big if it's sticky and it passes by one of those surfaces, finally hits the wall, it'll stick and stay. So that's the kind of the logic and the function there, how that works. Okay, another concept in the world of surface chemistry and understanding how and why and how this translates to something practical would be the concept of hydrophobicity and hydrophilicity. These would be very important for designing membranes, as well as things like adsorption, adsorbents and adsorption columns. So the contact angle is a concept where if you drop a bit of water on some surface, we can do that, it'll form some droplet, and the shape of that droplet will tell us something about how likely it is to stick on that surface. So you can imagine if I were to put a little droplet on my little piece of cloth, it's probably just going to disperse really quickly. Whereas if I put it on a nice glossy piece of plastic, like this little thing right here, it'll make a more round little bubble. And some surfaces will have somewhere in between. So you can see what this is showing us is actually a force balance between how the water or other liquid prefers to interact with the air versus the surface versus other water molecules. So that balance, there's actually three things going on, tells us something about how our liquid interacts with that surface. Tells us some surface properties there. So if we have a low surface energy surface, that means it's not really wanting to hang out with the water. And the water will bubble up more, and you see there's a 75-degree angle between the contact of our surface, and if you draw at that connection point right there, right where the bubble meets the surface, if you draw a straight line that matches the curvature there, that's your contact angle. Whereas if you have a high surface energy, something that's more hydrophilic, it will spread out further. And if you take cloth, typical cloth, you have lots of small fibers, lots of surface area, and generally it has this high surface energy. So unless you've made it like waterproof coating or something like that, it will probably spread out really quickly, and you won't even see the drop because it kind of disperses. Okay, so that's one way of describing some of the surface characteristics. This would also impact, well, does some other molecule have a favorable interaction with it? If water has a favorable interaction, then chances are good that something that is hydrophilic, something that is has some charge to it, or at least some charge polarization, is likely going to interact favorably with it as well. So it's likely that, let's say, some charged organic matter would end up sticking to this surface, but probably not so much to this surface, because this one is kind of repulsive to things that are like water or would like to be in water. So that's one thing we can do is describe a surface or some material as hydrophobic or hydrophilic based on that interaction. Another thing we can do, a similar process or similar analysis, would be to take a look at what's called the octanol water partitioning coefficient. So if we had some octanol and some water, they will phase separate. If we put some molecule in one of these, shake them up for some time, and then let them settle back out and separate back out, you will end octanol, and that gives us a 9-to-1 ratio, or however we'd like to describe it. Get some constant there, and we know, okay, that molecule is relatively hydrophobic. Or perhaps, in some cases, we might just call it nonpolar, because if it was more polar, it would probably be in water. So there's a few ways we can describe that. You can do that type of an analysis with more than just water and octanol, although this is the most common one. So you will have an octanol water partitioning coefficient. So if you ever see KOW, it's a good chance that's what it's referring to. And that's, again, giving us some consideration, measurement, some observation of how likely is a given molecule going to interact with other surfaces based on the chemistry, the surface chemistry of that surface. So a few tools I wanted to highlight here about how we can know what's going on at the surface. Okay, so with that, we'll get back to precipitation, which was kind of the original goal here. And I wanted to start there because many of the precipitation reactions will be forming particles, some of them charged, and allow us to catch other stuff. So I wanted to kind of have a starting point there so we can reflect on the adsorption we did talk about and kind of think about it, think about precipitation reactions and what's happening as we move forward. Again, a lot of this would be relevant specifically to coagulation and flocculation. One thing we often do, we will add alum, aluminum sulfate. That will add a lot of charge, to solution, destabilizing particles by shrinking the distance of that charge repulsion, and then they will start precipitating because when we have a lot of aluminum at the right pH, we will form aluminum oxide. So we add this stuff, and almost immediately it starts precipitating, forming particles, which actually helps us because we're then have larger particles to remove all of the particles with sedimentation. So we can use precipitation for removal of other metals, iron, copper, zinc, nickel, so on. If we can allow these precipitates to incorporate or include precipitation reactions of these other metals. So in addition to destabilizing the particles, we can get some other contaminants. And not even just metals, we could maybe do phosphate. For example, in some cases you can get what's called struvite, which is a combination of ammonia, magnesium, and phosphate. You can get that from wastewater. If the conditions are correct, sometimes it's a big nuisance for wastewater, and sometimes it's possibly a good benefit where you can say, all right, here's some nutrients we want to remove, phosphate especially, but also ammonia. And if we happen to have some magnesium in the water anyway, okay, let's remove that. So can be quite useful. We can use precipitation reactions to remove hardness, which would be calcium, magnesium, manganese too, but calcium and magnesium are the two that we generally think about for hardness. And again, for flocculation, right? And a lot of times we will accomplish some of these by doing a flocculation type of reaction, causing the precipitation, then collecting that afterwards. Ferric chloride is another one we use sometimes because that gives us an Fe3+. That turns out to be not very soluble. Okay, so how does precipitation occur, and how can we kind of see or model it is kind of an interesting question. So we're going to scrape the surface of it today, and I think next time we might go a little deeper on modeling it mathematically. But essentially we start with some solute. And how many of you have ever done the little experiment where you heat up a bunch of water, pour a whole bunch of sugar in it to oversaturate it, and then you cool it and crystallize it with like a string? Anybody else? Maybe? No? Yeah? Okay. It's kind of a neat reaction. I actually don't think I've done it myself, so I should do that. But essentially what you do is you get this super saturated solution by heating a bunch of sugar, and then if you just added all the sugar to the water, you'd have too much, right? And so some of it wouldn't dissolve. So that's why you heat it. You get it really hot, it all dissolves. Then you let it cool, and now you have a solution that has too much sugar in it, and it would like to precipitate, but if you keep it still and nothing's disturbing it, it tends not to have any crystallization. until you add something that kind of disturbs it. So you could probably toss some grains of sugar in there. You could probably toss some sand in there. But the typical experiment is to drop like a string in there and then let all the crystallization start happening because it has a seed. And we're about to explain that. And then it all starts forming crystals around that disruption. And it's kind of a self-propagating situation where now the crystals act as a solid that other sugar molecules can attach to and then form crystals around. So it's a kind of interesting. You start with a solute and you need some way to get to a cluster, but that's not a very energetically favorable thing to do unless there's something there, some surface already. So it's kind of hard to find the first surface. Then when you get big enough, you'll get some nuclei. And then depending on how the precipitation goes, you'll be having little blocks, molecules, building blocks of this crystal growing bigger and bigger in little chunks by chunks. So you can have homogeneous or primary precipitation, and that would be as opposed to secondary. And the nucleation, that's where you have chunks, and homogeneous is when you can achieve it without so much of a seed. So that might look something like this. This would probably be an alum addition. We see it's very orange. That's essentially, or that might be ferric chloride. At any rate, that's colored quite a bit because of this solid material, the minerals that we've added, but once it settles out, should be clearing up nicely. So any precipitation reaction will be driven by an equilibrium reaction. We've talked about this. So quick reminder, we'll step through the reminder for the H+, the water system as well. But we always set up our equilibrium reactions as products over reactants. And each chemical is going to go to the power of its stoichiometric coefficient. So if we have A solid in equilibrium with B plus C, that would end up looking like this: B to the B power times C to the C power over A to the A power. Always molar, and that's basically it. Of course, we could have A plus B and B plus C plus D on the other side, but that's not typical for a precipitation reaction, because precipitation we have one solid, right? The other key features here are if we have a solid, where we will often write it as S, then the concentration goes to 1, to unity, because it effectively, there's always more there. It's not having an impact on the equilibrium. So if there's solid in solution, it's effectively an infinite amount, is how we treat it for the equilibrium. So that just goes to 1. Likewise, the concentration of any liquid would also go to 1. So that means, for example, for water, liquid water in equilibrium with H plus and OH minus, the constant for water could be calculated as H plus times OH minus divided by 1, right? So you've seen that before. And what is KW? Yeah. So if you forgot, or if you're blanking, you should remember this one. 10 to the minus 14. It's pretty easy to calculate that, derive that. If you remember, at neutral pH, H plus is 10 to the minus 7 because it's pH 7. Then you can fill that in and say, well, neutral means there's equal amounts. So 10 to the minus 7 times 10 to the minus 7 is 10 to the minus 14. So you should be able to derive that. Just a reminder, that's also on this page probably. Just keep that in mind. Again, just a little more review here. We call these equilibrium reactions as reversible. So we can precipitate something or we can dissolve something, one way or the other. And usually both are happening at the same time. And when we find an equilibrium, that means because you are flowing water by it, and that water will not be saturated with the quartz minerals. And so pretty much anything will very, very, very slowly in some cases be going through this reversible reaction, but never go backwards if you are flowing water by it. So that's just a little glimpse into how this relates to geochemistry. And of course, some other materials will be much quicker, more likely, more soluble, and so on. Okay. Okay, many of these are pH dependent. Talked about them, I think, in the past. So one that we will be talking about shortly is chlorine. So keep that in mind as well, where we have the dissociation of hypochloric acid into H+ and hypochlorite. So this is the OCl-. And we would call this hypochlorous acid. That's also known as bleach, common free chlorine, right? Okay. Anybody want to pause, elaborate a little further here? We'll be making more use of equilibrium chemistry in this final section, so we'll have plenty of time, but just stop me if there's any questions. There's a nice little demonstration on the equilibrium reactions. I think, did we already talk about equilibrium reactions? Did we already do this semester? I think we did, right? Okay, so I have kind of a duplication of these slides, but so seen this? Yeah. So essentially what the point is, once we reach equilibrium, which usually we will be talking about after some amount of time, we've reached some equilibrium, then it's not necessarily the case that the rates are that the amounts are the same, but the rates should have reached the same, and that's our equilibrium. So the rate going down equals the rate going up, or the rate this way equals the rate this way, right? However you want to look at it. And then the K, our equilibrium constant, would kind of be showing the difference, the ratio there, of the products versus the reactants. Okay. So, example of that, may or may not have talked about, I don't think we've talked about this one yet, but the carbonate system, we could recognize we have several Equilibria reactions here. We have carbonic acid, H2CO3, in equilibrium with giving off a proton, and our bicarbonate, HCO3-, which would then be in equilibrium, and of course that would be just the HCO3 would be in equilibrium with, so pardon my shorthand here, with H+ and carbonate, CO3 2-. So we could then recognize and use plots like this to say, oh, okay, well, what fraction of our system, of our total carbonate, is in carbonic acid if our pH is 5? And the answer to that, we could just simply draw here. Well, if I drew that straight, we would find something like 95% of it. Okay. We could also recognize that we have these points here and here, where two species are equal. Those are going to be our Ka values, Ka1 and Ka2. So the acid dissociation constants, or equilibrium constants between these two at pH 6.3, something like that. There's the same amount of carbonic acid as there is bicarbonate. At pH 10.3, approximately, there's the same amount of bicarbonate as there is carbonate, right? And if you had my other class last year, you've seen this too much. So does this make sense? Everybody seen this before? Good. All right, so continuing with this little reminder segment, pH, already challenged you. Kw is 10 to the minus 14, and you can derive all of that recalling that the p is a log function. Take the negative log of x, and you have px. So pH of 7 corresponds to 10 to the minus 7, which would be our H plus concentration. Okay, so kind of back to the solubility, now that we have a little equilibrium refresher in case you needed it. We can take a look at all sorts of different minerals to see, well, how soluble or insoluble are they? And if we stop and think about it, if we set up our solubility product as the products over the reactants, and we set it up so that our reactant is the solid, and the products would be the dissolved species, that's convention. So we'll have a solid on the left side and the products on the right side. That means we're going to have some K that is divided by 1, which is quite convenient because the solid becomes 1. So anytime we have these, the equilibrium equation, or the constant, will be equal to the resulting dissolved species multiplied by each other with any exponents necessary. So, for example, we'll take aluminum hydroxide, AlOH3. This corresponds to Al3 plus and 3OH minus. Okay, so when we dissolve that, or when that's in the water, we can take a look, and the solubility constant, or the precipitation constant, would equal essentially the concentration of Al3 plus, and the book here is using activity, don't worry too much about that for now, times OH minus to the third power, right? And so this number we can see is a very small value, something times 10 to the minus 32, because also notice that this is corresponding here. So 6.31 times 10 to the minus 32. So what this is telling us is a very small amount of this will be in the dissolved form, meaning most of it will go to solid. Okay? So with that really, really small number, what we recognize is if there is any OH minus around, it is very, very favorable for this to form the solid. So when we add our alum, if we're at all near neutral or basic, it's going to be taking our hydroxides and forming this amorphous aluminum hydroxide. So when we add alum then, aluminum sulfate dissolves pretty well. I don't think we have it listed here, but it's quite soluble. Then we have aluminum hanging out in water, and if our pH is correct, or maybe we need to adjust it a little bit, add a little bit of base, suddenly we get a lot of amorphous aluminum hydroxides precipitating. So we could look at some other minerals. Gypsum, for example, is quite a bit more soluble. Not like super, super soluble, but much more so. And we could see, some range of them. It's a ferrous sulfide. It's pretty soluble comparatively, and so on. Okay. This is probably also why sulfide, is not so great for our plumbing when we have wastewater with it in it. I don't know what my computer's doing. Okay. If we have iron reacting with sulfide in the water, then we have some iron sulfide mineral, then it dissolves and goes away, right? So it's a way to dissolve our metal pipes if there's iron in it. We'll be attacking it, so to speak. Okay, so let's come back to precipitation and take a look at it in terms of thermodynamics. We can describe these rate constants in thermodynamic terms. So when we get an equilibrium constant, we can relate that to essentially the forward and backwards reaction rates, the rate of dissolution compared to the rate of precipitation. And we can look at that from a thermodynamic perspective. So we can then apply the Van't Hoff equation, which is done already, and say, well, what happens if we change the temperature? Normally, we'll do things in standard temperature, but as you know, we talked about sugar already, that precipitation reaction, how much sugar can we dissolve is temperature dependent. We can heat up the water and suddenly we can dissolve more sugar, right? That means our solubility has increased. That solubility product became a larger number and in a temperature dependent manner. So we could describe K as the exponent of, what is going on with my, so weird. Okay. Sorry. We can say K is equal to e to the minus delta G naught divided by RT. So this is coming from the standard Gibbs free energy. R is the universal gas constant. T is absolute temperature. It's coming from our conventional thermodynamic equation where Gibbs free energy would be equal to the delta enthalpy minus the delta entropy, or T delta S rather. So if this is Gibbs free energy is G, this is enthalpy, and this would be our entropy term. Okay, so we could, for a given reaction then, calculate each one of these and find some value and essentially solve for a missing component or solve for a new K given the situation. Okay, makes sense? Any issues there? Stuff you've seen before, for sure. So, when it comes to nucleation, I want to know at what point is it favorable, right? With the sugar example, at some point we were able to start the crystallization, start that precipitation of solid sugar. So if we take a look at the free energy change, delta G, and plot that as a function of how big our little particles are, we could see that some particles, the very small ones, the delta G is very big. So let's see. Trying to remember. Might have to go back to the book and remind myself what the SS is. Anybody see what this might be? I'm blanking. I think this might be the number of nuclei that are already there. No, this is by size. Okay. I'm sorry. I'll have to come back for you on this one. One thing I'll point out here, and I think this has to do with the number, perhaps the number of reactions that are already there. But one thing we see in most of the cases, once we have some momentum occurring already, maybe this is the number of particles in solution or per some volume. But as we increase the radius, it's the important part, the diameter of these particles, the energy becomes, to form a new particle becomes much, much smaller. And so what this graph is kind of revealing to us is why the sugar was not just automatically doing it. There's not really much to grab a hold of. It's a difficult thing to do thermodynamically. But once there are many particles and you start growing the particles, that energy falls off. That kind of that free energy or that activation energy required. Yeah. Thank you. Okay, so it's how supersaturated the system is with respect to the solute, right? Okay. Okay, so then we see here the right figure is showing this is a PSD function, particle size distribution function. So the number of particles per liter, and it's showing the size of the particles. So if we seed the system and we have the nucleation happening, we get a large spike in particles, smaller particles than we, or I guess particles around 10 micrometer. Whereas if we don't seed it, we don't get all the extra particles forming, is kind of the point here. So all this to say, even if we are supersaturated, there's still some energy barrier. And once we overcome that, or we can overcome that if we begin adding more particles to seed it to begin with. Okay. So one thing we can do with the thermodynamic approach is we can build solubility plots and use solubility plots to understand what pH is, under what conditions, what concentrations, will we have different species. So speciation diagrams can be quite useful, can be quite important. We can build them from the equations that we can get from here, and from kind of these equations to say, okay, here's our K. Our K corresponds to Al3 plus times OH minus to the third. And if we take the log of those types of equations, we can start plotting segments on an equilibrium diagram like this. So we can take the log of concentration versus the log of pH and essentially take a look at where will copper be in the soluble form. So aqueous copper might dip all the way down to here, meaning we are least soluble here, whereas if we had superacidic conditions, more of it would be dissolved. So we might aim at some treatment goal. Anywhere in this pH range would achieve that goal with this condition. Another thing we'll notice is the total copper in solution in this case, if this is log of the molar concentration, which probably would be, then that would mean we have 10 to the minus third moles per liter of copper. Okay, so we can kind of see that, read that from the plot. There's no other higher mark, so this, and this is the total, this thick line is the total copper. And so in different spots we could discern, okay, what phase or what form of copper do we have? Many times it'll be a mixture, but if we're really concerned about the Cu2+, you can see that line here. We just make sure we are high enough pH, and at least we don't have that one, right? At some point we will get so high pH that we have other dissolved forms. Maybe that's bad too. So there's a lot we can do with these plots. We can build them from our equations that relate each type. So for some portion of this diagram, we could relate the copper 2+, and relate that, of course, with pH, but then compare that with the CuOH2. And at some point, the copper 2+ will dominate, and then at some point, the CuOH2 will start dominating and be the primary factor that's affecting our total, or the predominant type. Okay, this holds true for many precipitatable solids, many minerals. So zinc, for example, here we have it around pH 10, is pretty insoluble, or we have products that are quite insoluble. And so this would be the equilibrated with amorphous zinc hydroxides. Okay. And we could see, you know, one of these plots on the left. This is our total, kind of goes up to the most that the solution could possibly have. On the right, we have some discrete amount. So we have 10 to the minus 4 moles per liter, so 3 times 10 to the minus 4 in this solution. So that's capping out at some point. Total zinc should be 3 times 10 to the minus 4. Looks like maybe they have an axis issue, but anyway. So, make sense? You seen these before? So. The location, the height will depend on it, right? So, in the case on the right, you'll have it plateau here, and even though I think maybe it should be plateauing more like, so they say 3 times 10 to the minus 4th. I think it probably should be plateauing here if they drew it. It would look like the same plot, just plateauing there, right? So you could consider having more or less, but it should have the same shape. Now the one on the left, this is in an ideal solution equilibrated with amorphous zinc hydroxide, meaning there's a perpetual amount of solid in there that could dissolve if you give it conditions to dissolve. So even at the very, very low pHs or different conditions, you'll find you have plenty of it. And if you look at the pH scale here, we're going down to 6, whereas this, well, I guess we're going to 6 on both. Okay. So instead of reaching a plateau, since we apparently still have zinc hydroxide here, solid, it's essentially giving more zinc to the solution because we just have so much zinc hydroxide. It's almost as if we made a swimming pool out of zinc hydroxide, put this water in it, and however much is needed is just coming off the walls, right? So that means we get a very high amount of zinc because we're in equilibrium with it. Okay, so that gives us a couple ways to think about and to draw these. Whenever we have that equilibrium with something that's dissolved, or that's solid, excuse me, it won't be quite so plateau-like. It'll be like, okay, now this one dominates, and then this other one dominates. We're not gonna like reach the total, whereas we do reach a total if there's a discrete amount. In this diagram, for example, once we are here, I don't think we have a solid phase or much of a solid phase anymore. So this guy, even at pH 6, this is 10 to the minus 9. So there's very little solid here, whereas on the other diagram, there's still plenty of solid. Okay. So just a couple examples, just to kind of wrap up a little bit. Flocculation is used in sedimentation, where we will have sedimentation basins. It's kind of what it might look like when we gently stir and let particles get bigger and bigger. That's what we call flocculation, and then that promotes the sedimentation. I also mentioned the granular filtration. So one step we often do in drinking water treatment after a coagulation flocculation step would be to filter our water through granular media. These larger destabilized particles, even if they fit through the pores, they would then be sticking to the media, and we'd accomplish our treatment in that manner. If you are ever curious, I do have a little pilot demonstration system in my lab, so you can kind of see what the granular media would look like. In this case, these are loaded with what's called green sand plus, which has some manganese coated sand in addition to some just anthracite. So mixed media there. And that can do a decent job removing things like arsenic, manganese, because it interacts well, and iron. Okay. Speaking of iron and arsenic, another way we could look at these, and do sometimes look at these things, would be, instead of a log concentration versus pH, we could look at essentially the oxidation potential versus pH. So EH versus pH is sometimes how we describe that. And we could find under what conditions, what kind of oxidation conditions, redox conditions, we'll talk more about redox, under what conditions do we have different species. So in some cases we could have major changes across pH, or major changes across the oxidation potential of the water. Eventually, if we make it super, super oxidizing, we will convert water to oxygen. And if we make it super, super reducing, we will be reducing water to hydrogen gas. So those are kind of the upper and lower limits. And you'll notice those do depend a bit on our pH. We have more propensity to form hydrogen when we have more H+ around in solution. And reverse is true for the propensity to form oxygen. So looking at the, so arsenic is a little more complicated, lots going on there. If you were particularly interested in one form of arsenic, you would identify, okay, what are the conditions that we can be forming this? What pH do we need to be? How oxidizing do we need the conditions to accomplish that transformation? So we'll take a look at the iron here on the right. A little simpler. We can see that Fe3+ doesn't really occupy much territory where it's stable in solution. Has to be fairly oxidizing to keep it at 3+, and a pretty acidic condition for that to be simply hanging out there as Fe3+. It would much rather become FeOH3, for example. So when we add ferric chloride, that's going to add Fe3+, and almost instantly, it's going to be trying to form iron hydroxies, FeOH3. Likewise, Fe2+ is can be around even to neutral pHs, but if it's a bit oxidizing, it's probably going to shift over, become oxidized, and end up forming these iron hydroxides. Or perhaps if we are in a basic condition, not super oxidizing, maybe it'll stay as Fe2+ and form an FeOH2. So different things we can consider there. And the same type of deal goes for arsenic, same type of deal goes for any of our solubility equilibrium systems. A lot to think about, a lot to potentially do, and we often use software that has these relationships built into it if we need to really do deep work on solubility diagrams and all that. They're also called poor boy diagrams, the log C versus pH, after somebody who developed these. Okay, last thing I wanted to mention is another application where we use precipitation reactions. Here's a rundown of how we do water softening with by making use of solubility to pull. Really what we're trying to do with water softening is get calcium and magnesium as the primary tasks. Sometimes if there's other multivalent cations, they might also come out with the same type of reactions. So the way we do it is we essentially encourage the water to have conditions that favor precipitation of calcium carbonate, magnesium hydroxides, and we kind of cycle between promoting those two. And so we'll end up in a water softening process, we will end up with sludge consisting of calcium hydroxides, calcium carbonates and magnesium hydroxides. So first of all, we have to get rid of CO2, any extra CO2 from the water, and we can do that because we know that if we add, and the reason we need to get rid of it really is because we want to get rid of not just the calcium carbonate that's there already, but we want to get rid of the excess calcium also. So it's a bit of an iterative process. We try to get rid of CO2. We can actually add calcium hydroxide, which sounds weird because we're trying to get rid of calcium. We're adding it. But that'll get us calcium carbonate. Then we remove what we call calcium carbonate hardness. So in this first one, we're adding 1 calcium to remove 1 calcium, but we're also removing carbonate in the process. Whatever is left, we can remove the calcium carbonate hardness by now adding CO2. Kind of a strange sounding process, but it does work. So we're going to add bicarbonate and more lime, and we'll get a corresponding amount of calcium carbonate solids. So we are first targeting CO2. That comes out here. Then we are targeting calcium 2+. And what we have to do is add some extra, but what we target is coming out here. So each time we are targeting something and causing it to precipitate out. Then we move on to magnesium, kind of the same process. We've already removed the excess CO2 though, and now we're going to do this by catching what we call magnesium carbonate hardness. So we're adding magnesium. No, excuse me, we're not adding magnesium. We're adding bicarbonate. Sorry, I'm misspeaking. We're not adding any bicarbonate in either one, I think. It's just how much is there. We're adding the lime. Whatever bicarbonate is still there after we removed some CO2, that will form our calcium carbonate and magnesium hydroxide. I'm not planning to quiz you on this. Maybe we'll do more on it. My point overall is we're using these precipitation reactions to target some dissolved species and getting it out. So I'm just going to wrap up pretty quick here. Sorry for the misspeaking there. Second to last, we're going to get the calcium non-carbonate hardness by adding, now we're adding soda ash. So now we're adding carbonate back in order to get the remaining of the calcium that's there. Finally, we're going to get the remaining magnesium by adding lime and soda ash. So this whole process is called the lime soda ash softening. Those are the two things we add. If we do it in the right order, we end up precipitating more and more of the calcium and magnesium. Now, all of these are precipitation reactions and therefore equilibrium reactions. So there is a limit, and I think it's around 30 milligrams per liter as CaCO3. It's how we measure the hardness. So we cannot make it softer than approximately that because the chemistry just simply won't support it. So there are other ways to soften it further if we had to, but for drinking water, this is usually plenty good enough, and that's pretty soft water. We generally consider water with that equivalent of about 50, 60 range or less as soft water. So that is decidedly into soft water territory. So if we had hard water, added this treatment, essentially what we're doing is we're converting this dissolved stuff to solid sludge stuff that we can just precipitate, so we can collect them, dry them, landfill them, or find a purpose for them, and we're good to go. Okay, so that's precipitation for you. I think next time we'll do perhaps some problems with it. Any questions before we go? All right, so I'll see you on Thursday.